Hello and welcome. This is Dr. Jeremy Mandelkern of drmtutoring.com, and today we're going to be looking at rates of change. If you like this video, feel free to click the like button. You can comment in the comment section. You can also share this video with your friends and classmates if you find it would be helpful to them. There are worksheets available in the comment section of the intro video, including this one. So in this worksheet, we're going to be looking at rates of change, in particular, two different types of rates of change. The first is an average rate of change, and that is just a slope calculation for some secant line that passes through a given function at two different points. The second is called an instantaneous rate of change, and this is going to be representative of the slope of a tangent line at a given value for the independent variable. We'll later see that the instantaneous rate of change is nothing but a derivative calculation at a given value for the independent variable. Let's try this first problem. It reads, given the function f, find its average rate of change between the points x is 1 and x is 5. Well, for notation, we represent such an average rate of change as a delta y divided by a delta x. In the numerator, we have the function value at the endpoint of the independent variable interval. So that would be f of 5 minus the function value at the initial point of that interval. And this is going to be divided by what is the difference of the two values, endpoint 5 minus initial point 1. So you'll recognize that notation as being nothing but a slope calculation, and indeed it is. In the numerator, f of 5 appears to be 75. F of 1 appears to be 11. In the denominator, we have just 4. The subtraction in the numerator returns 64, and hence we get an answer of 16. We can potentially check our work using a rise over run slope calculation for the slope of the line through the points 1, 11, and 5, 75. Of course, the calculation will be identical. Let's try the next one. In this next problem, we're tasked with finding the instantaneous rate of change of a given function f at the value x is 1, and we are to do so by two different methods. These two different limit definitions for the instantaneous rate of change. Let's try this first one. So here we have what is the limit as h goes to 0 of. In the numerator, we're going to first replace the x in f of x by a plus h. It's important to understand here that a is a fixed value given to us as 1. So we get then what is the quantity 2 times what is 1 plus h squared plus 3 times 1 plus h plus 1. And we are to subtract f of a, which by inspection is nothing but f of 1, which is 6. In the denominator, we have h. Next, we'll simplify so we can perform some algebraic operations in the numerator, squaring out the 1 plus h, distributing the 2 into that result, distributing the 3 into the 1 plus h. When the dust settles and the smoke clears, what remains in the numerator? It'll be some polynomial in the variable h. By inspection, there is a 2h squared. There's also a plus 2h times 2, or plus 4h, plus 3h, so plus 7h. As far as constant terms are considered, we have what is a plus 1 times 2, so that's a plus 2. There's also a plus 3. There's also a plus 1, so it's plus 6 and minus 6. In the denominator, we have h. Please note that the plus 6 and the minus 6 are canceling, and we can then divide out a common factor of h. So we get just the limit as h goes to 0 of looks to be 2h plus 7. And this limit is evaluated directly by replacing h by 0. It gives us the value 7. Let's go ahead and try the alternative formulation of the instantaneous rate of change. So here we have the limit as x goes to the a value 1 of, in the numerator, we'll go ahead and simply write the function f of x. So that is 2x squared plus 3x plus 1. And we are to take away f of 1, which we know to be 6. In the denominator, we have x minus 1. This will be an indeterminate form if you try to evaluate directly by, say, replacing x by 1. You would get 0 over 0. So the next task is to try out those algebraic techniques. Can we simplify the function before we apply the limit? Well, it turns out we can. So in the numerator, we can factor, and unsurprisingly, the troublesome factor of x minus 1 that's in the bottom is also a factor of the top. The other factor appears to be 2x and perhaps a plus 5. Please verify that if you multiply out the product of the two binomials in the top, x minus 1 times 2x plus 5, you really do get 2x squared, and you get plus 3x. And you also get a minus 5, as we should. Now we can cancel out the x minus 1s and just apply the limit to the simplified function. So it's the limit as x goes to 1 of 2x plus 5. Unsurprisingly, this is also equal to 7. As a final check of our work, we'll use slightly more advanced methods. The derivative of the given function f computes to be 4x plus 3, and the m value that we were seeking using two different methods in this problem is nothing but f prime of 1, which is 4 plus 3, which in turn is 7. So this is an independent check of the results that we obtain. Let's try this next problem. It reads, given the function f of x is equal to x cubed, find the instantaneous rate of change at the point x is equal to 2, and do so using our two different methods. First, the limit involving h going to 0. So here we have the limit as h goes to 0. We'll draw a big division bar. In the denominator, just an h. And in the numerator, with a being 2, we wind up with f of a plus h looking like 2 plus h cubed. In the term minus f of a, I suppose we can just evaluate the function at 2 to get an 8. Now, the next step is going to be simplifying the numerator. We're going to use the binomial theorem, which provides a method to expand out counting number powers of binomials, like a plus b to the n. You can look this one up in a reference book. I will go ahead and apply it directly. So the binomial theorem is a handy theorem to put in the pocket for when you need to expand out powers of a plus b. We wind up in this case with a binomial coefficient of 1 times a 2 cubed plus a binomial coefficient of 3 times a 2 squared times an h plus another binomial coefficient of 3 times a 2 to the power 1 times h squared, finally, plus the binomial coefficient of 1 times h cubed. And there's still that minus 8 in the top. We have an h in the bottom. I have made a cardinal sin, unfortunately, though. I have forgotten to write my limit. We'll just edit this out. So this is what that will look like when we use the binomial theorem in the numerator to expand out 2 plus h cubed. Now, the next thing to do is to simplify. Please observe that there's nothing but a polynomial in the variable h in the top. And we can go ahead and perform all the algebraic operations up there to write it as such. It observably has no constant term since there is already a 2 cubed with a positive sign in front and also a 2 cubed in the form of a -8 with the minus sign in front. So these terms are canceling. And thus, it's going to be just a polynomial in H where there is no constant term. Observe that when we simplify in the numerator, we're going to be getting what is a single H cubed. There is by inspection plus 6H squared. There's also a plus 12H, and the constant term is gone. Please observe that we can cancel out the H's. There's a common factor of H in top and bottom. So we just wind up with the limit as H goes to 0 of a quadratic polynomial in H. It is H squared plus 6H and plus 12. This limit is 12. Let's try this next one. It reads, calculate the instantaneous rate of change, but using this alternative formulation using a limit. So here we'll go ahead and write the limit as x goes to the a value, in this case is 2. Observe that in the numerator, it's a little bit different. So we have f of x, which is nothing but x cubed, minus f of a, which is 2 cubed. So that's 8. And in the denominator, we have x minus a, or x minus 2. We can go ahead and apply the difference of cubes factoring formula in the numerator to get the limit as x goes to 2 of, and it looks like we're going to wind up with x minus 2 times x squared plus 2x plus 4. And in the denominator, we have x minus 2. Aside, we've made use of that handy formula, which is a cubed minus b cubed is equal to, which is equal to a minus b times a squared plus twice ab b squared. Okay, next we'll go ahead and cancel out the common factor of x minus 2. And we'll simply apply the limit to the simplified function. When we do so, it's just the limit as x goes to 2 of x squared plus 2x plus 4. Because polynomial functions are continuous everywhere, this limit can be evaluated by just replacing x by 2. Hence, we get 4 plus 4 plus 4, which is 12. This agrees with the value we obtained earlier using a slightly different limit formulation. And as a final check, we'll go ahead and compute the derivative using slightly more advanced mathematics, something called the power rule. We wind up with 3x squared, and the m value is nothing but f prime of 2, which is 3 times 2 squared, which is 12. So that agrees with the value that we obtained before. And with that, we finished yet another calculus worksheet. I hope you enjoyed this video. Feel free again to click the like button if you haven't already done so. You can subscribe to the channel and share the video if you think it'll be helpful to your friends and classmates. This is Dr. Mandelkern saying thanks and goodbye.